Okay, let's start with the worksheet number 2. Okay, in this worksheet, the first question is that you have to represent the BCD using packed and unpacked form. Okay, the number that is given to you is 1, 3, 4, 5. So I have already done the working over here. So in unpacked form, what we have to do, suppose we have how many numbers over here? How many digits? 1, 3, 4, 5, 4. So you will be representing each digit using one separate byte. Okay, so for the first one, suppose I have written here, this 1 is actually represented by these values. What is the binary equivalent for 1? It is 1. And for making it 1 byte, I will write the rest 70 on my left hand side. Okay, similarly, the binary value for 3 is 11, and rest I will write 6 zeros on my left hand side to make it 1 byte. Similarly, 4, this is the equivalent value for 4, 100, and the rest zeros are representing they are used to represent one whole byte. Similarly, 5, for 5, the binary value is 101, and I will write the next all 0 over here to represent 1 byte. So in the unpacked form, what you are going to do, you have to represent each single digit using 1 byte. And in the packed form, what you are going to use, you can represent, suppose I have given here 4 digits, so I will take 2 digits here and I can represent 2 digits using 1 byte. So for 1 digit I will be using 4 bits over here. Okay, this is representation of 1. So actually 1 can be represented by in binary using the 1 value, and rest 3 are for representing it into a 4-bit form. Okay, and then 3 is represented using 11, and I'm adding 0 on my left hand side to make it 4 bits, right? Similarly, so together 4-bit and 4-bit they become 1 byte, right? So I'm taking here 2 digits together and I'm representing them using 4-bit each, right? And similarly for 45, I am going to represent 4 over here and 5 over here, right? So this is my packed form. Okay, in question number 2, what we have to do, we have to add these two numbers using BCD. So just a small recap of BCD. BCD stands for binary coded decimal, and where each digit is represented by using a binary code starting from 0 till 9. Okay, so they are basically used for representing the digits in the digital clocks or simply in your handheld calculators. Okay, so let's solve this question. So we have given the value 0.26 and you have to add it with 0.85. Okay, first of all you have to write the equivalent value for each digit. So for 0, okay, I am going to write 0000. I am going to represent it using 4 bits. Okay, for 2 it is, the equivalent value for 2 is 0010. Okay, and then for 6 we can represent the 6 by using 0110. This is the actually equivalent code for 0.26 in binary. Then the next digit is 0.85, so I'm going to write the 0 value over here using 4 bits. And for 8 I can write 1000, and for 5 I can write 0101. Okay, then next what I have to do, I have to add these using BCD. So in BCD, what I have done, first I have converted each value into its binary equivalent, right? And then I'm going to add them. Okay, so what is my answer over here? I'm going to use this textbook because it gives you a neat look over here. So I'm just moving it here so that you can also see the calculation over here. So 1 plus 0 is basically, what is the answer? 1 plus 0. So okay, now it's hard for me to type here, so I'm going back to here. Okay, 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0 over here, and carry over here. Okay, and it becomes 1. Okay, so 0 plus 0 is 0. Okay, so next 1 plus 0 is 1. 0 plus 0 is 0. And this 1 plus 0 is 1. And rest 0.000 and 0. Okay, so final answer I got is, this is also 1 over here. Okay, so I got 0, 0, 0, 0.1000 1 0 1 0 double 1. Okay, so this is the answer I got in BCD. Now let me cross check. If I add 0.26 with 0.85 in maths, what answer I get? 6 plus 5 is 11, 8, 19, 11, and 1 carry is 1.11. Okay, I'm getting 1.11. Okay, now check what are these values equivalent to in binary. This is 0. Okay, so if I assign them power, I have 1, 2, 4, and 8. Okay, so if I add only ones, I have 8 plus 2, 10. Okay, and if I give them power 1, 2, 4, and 8, so I have cross out the 0 and 8, 19, 11, right? So here I get 0.1011. But in maths, I got 1.11. So what's the difference? There's a huge difference. I'm not getting this answer, 1.11. When I converted these binary values back to Denry, I'm getting 0.10 and 11. So this answer is incorrect. Why? Because in the start I said that BCD is capable of representing the values starting from 0 till 9. Okay. So it cannot represent any value that is greater than 9. So here I'm getting 10 and 11. So that's the problem. So whenever you get a value that is greater than 10, so what you have to do? You have to subtract it from 6. Why 6? Because BCD is represented using 4 bit. How many bits? 4 bits. So using 4 bits, how many total digits I should be representing? I should be able to represent total 16 digits. Why? Because BCD is represented by using 4 bits. So I have used here 4 bits, 4 bits, 4 bits to represent each digit. So 2 raised to power 4 equals to 16. So I should be able to represent 10 and 11 and 12, but I'm not because BCD can only represent the values from 0 till 9. So total it is representing 10 values. So here comes the problem. So if you get any value that is greater than 9, okay, so what you have to do? So to compensate these values, what we will do? We will add the value of 6 in the answer that we get. Okay, so we got, let me solve over here. We got 0.10 and 11. Okay, we got this answer. So let me write this equivalent value in BCD using 4 bits. 1, 2, 3, 4. So equivalent value for 10 was 1, 0, 1, 0. And 11 was 1, 0, double 1. So what I said, to compensate the problem, we have to add the equivalent value of binary value of 6 in this answer. So the binary value for 6 is 0, double 1, 0. Okay, I'm gonna add this. Okay, so 1 plus 0 is 1, 1 plus 1, 0, carry over here, zeros as a sum, carry over here, 1 plus 1, 0, and this carry goes over here, so it becomes 1, 1, 0, 1.0, 2, 3, and 4. Okay, now see, what we were supposed to get? 1.11. Now compare this value. What we got here? This one is equivalent to, we were supposed to get 1.11. Let me write over here. We were supposed to get this, isn't it? Okay. Okay, so we got this 1 over here. Okay. Okay, this is 1. And by the way, don't read it as 11. This is not 11. Because in BCD, we don't have any 11. We can only represent values from 0 till 9. So you have to treat each digit individually. So this is 1 and okay, I got this 1. So this is correct. So I also should get 1 over here. But what I am getting? I am getting 1, 2, 4, and 8. So I am getting 8 plus 2, 10 or 11. I'm getting this value 11. Okay, but I'm getting 11. What I need? 1 over here. Okay, so now I have fixed this part. I got 1 over here. This is the equivalent representation of 1 over here. So I need to fix this part. So what I can do, I can again add the equivalent value of 6 over here. Okay, so what is the equivalent value of 6? 0, 1, 1 and 0, right? And I'm gonna add it again. So 1 plus 0 is 1. 1 plus 1 is 0 over here. 1 carry, 0. 1 carry, 1 plus 1 0 and carry over here. So this will become 1 triple 0 and I'm putting point over here, and also I'm copying this value over here that is already solved by me. So I got, okay, now you compare this value with this one. This is equivalent to 1, this is equivalent to 1, this is also equivalent to 1. So we got 1.11. Okay, so this is our final answer in BCD. Now this is the correct representation of BCD. Okay, the next question is that the ASCII code for A is 41 in hexadecimal. Calculate the ASCII code in hexadecimal for Z. Okay, the ASCII code for A is 41 in hexadecimal. Okay, so what you have to do, this question is a little bit tricky. The 41 value is given in hexadecimal and you need to figure out the value for Z, right? So what you have to do, first you need to convert this 41 into its equivalent decimal, right? So how you will convert into decimal? So you have to multiply it with 16, 4 into 16 plus 1 into 16, and then you have to give them power 0 and then 1. Okay, and 16 for the 64 plus 16 raised to power 0 is 1, so 64 plus 1 is equals to 65. Okay, so we sorted out that the hexadecimal value for A was 41. Now in decimal it is 65. Okay, so they're asking you to calculate the value for Z. So how many digits we have in English from A till Z? We have in total 26 letters from A till Z. Okay, and the first letter is being calculated. Its value 65. Rest how many are left? 25. Okay, so according to our knowledge, if I add 65 with 25, because the first letter I know the answer, it's 65, so I've been left with 25 letter. So 5 plus 5 is 10, 6, 7, 8, 9. So the decimal value for Z is equals to 90, right? This is the decimal value. But what I have to do, I have to find out the hexadecimal value, not the decimal value. So first I found out the decimal value, that is equivalent to 90. So now what I can do, I can apply my knowledge of converting the decimal number into hexadecimal number. So how do we convert the decimal number into hexa? Simply by dividing it with 16. So I will divide it with 16. So 16 5s are, and I get 16 5s are 80, and remainder I get 10. So I can represent in hexadecimal 5, and 10 equivalent is A. So for Z in hexadecimal is equivalent to 5A. So we can also check it in our book. In book C, character A, which was given the value of 41 over here, its equivalent was 65. Okay, and I added 25 more and I got 90, and when I converted this 90, the decimal value into hexa, I got 5A. Okay, so both are same.